Hello, everyone, and welcome to the Rates Part 2 edition of our GMAT Ninja Quant video series. It's so great to have you with us. Before we dive into some questions together, I want to talk first about whether this video is for you and what exactly we'll cover in this video. So let's go ahead and dive in. First, about whether this video is for you. There are a few reasons it could be for you. Number one is if you know rate fundamentals but struggle with everything else. We actually covered rate fundamentals in a previous video where we went through conversions and rates part 1. So if you do struggle with the rate fundamentals or want to learn more about that, then you can check out that video. We touch on those fundamentals. In this video, we get into some quirkier things, which doesn't necessarily mean harder things, but it does mean a little bit quirkier things. So if you want to drill down on those fundamentals, you can see that in our conversions and rates part 1 video. Secondly, this video could be with you if you're intimidated by anything other than basic rate problems. We see students like this all the time where if they see anything other than a basic rate problem, their brain just kind of melts. And finally, if you don't have a consistent approach to rates, we will give you a consistent approach to rates in this video. Next, I want to talk about what we'll cover and several different things that we'll go through in this video. Number one, we'll talk about those identical machine questions. So we'll be sure to go through a question like that where we'll talk about what to do with identical machines that are working together. We'll talk through the catch-up questions, right? So-and-so started so far, got so far ahead, and then somebody else comes to try and catch up behind them. We'll talk about the question that you often see about trains colliding. We'll touch on average speed, how to use logic with rates, and then we'll also talk about converting word soup into algebra. So all that will be covered in this video. And again, this word soup, because this is part of the word problems subsection of our quant video series. Also, a couple other things to remember is that, like I said, this rates part 2 is not necessarily harder than rates part 1. There were some pretty hard questions towards the end of our conversions and rates part 1 video. And then also on top of that, remember that the fundamental skills behind rates are really, they're pretty basic, they're pretty straightforward, and you can do some weird stuff with it, but it's not, at the end of the day, it comes down to some basic stuff. So we'll see that a lot throughout this video. And like I said, we covered the basics in a previous video, so you can check that out if you want a video on the basics. But with that in mind, I want to go ahead and I want to dive in to the first question that we're going to look at together. I'll go ahead and I'll throw this question up on the screen, and then I'll give you a second to work through it, and then we'll come back and we'll discuss it together. Awesome. So hopefully you've had a minute to work through this one here. I'll go ahead and read the question, then we'll talk about it together on the board. The question asks, how long does it take a hose to fill a bucket containing m ounces of water? Statement 1 says if the hose poured water 10 times faster, it would take 4 minutes to fill half the bucket. And statement 2 says the hose poured 64 ounces per minute. Like I said, we'll go ahead and first we'll take a look at this one on the board. And what I'm going to do first is I'm going to remember that with every rate problem, the basics or the fundamentals of rates are always going to start with that the distance is equal to the rate times the time, or that the work is equal to the rate times the time. Work is a little bit more appropriate in this instance, but distance is just a form of rate when you have those sorts of problems. But anyway, what I'm told from statement 1 is that if the hose poured water 10 times faster, it would take 4 minutes to fill half the bucket. And so what I'm going to try and do is I'm going to try and organize that information in some form like this. But before I do that, I know that I can say from the question that m ounces is equal to the rate, and I'm going to put sub h for the rate of the hose, times t, and I'm trying to determine what t is. So t is going to be equal to m ounces over the rate of the hose. Now, statement 1 tells me that if the hose poured water 10 times faster, so in other words, I'm going to say 10 times the rate of the hose, it would take 4 minutes, so I'm going to say times 4 for the time, to fill half the bucket is equal to m over 2. And there I've translated all the information that I'm given from statement 1 itself. From here, I'm going to remember that my question was asking me what is the time equal to, or I could reorganize that as what is m over rh equal to. And what I noticed real quickly here is this, is that I can actually solve for m over the rate of the hose, because m divided by the rate of the hose, if I divide both sides by the rate of the hose, and then also multiply both sides by 2, is going to be equal to 10 times 4 times 2, or is going to be equal to 80. So the time required then to fill the bucket is going to be 80 minutes. Now, you can see there are a couple key takeaways. Number 1 is pushing the question here, because something that was super important was that I solved, I didn't just say, many students will just go right away and they'll say, okay, I need to solve for time. What's my time equal to, right? And when you do that, it's not quite as obvious when you get to this stage that, hey, I actually can solve for the time here. And I'm actually able to do it. So pushing the question to this stage is super important. And then obviously taking the information that I'm given and putting it in a form that I'm familiar with is another really good takeaway from this question. Statement 2 says this, that the hose poured 64 ounces of water per minute, which from there, well, let me go ahead and cross out B, C, and E because I've narrowed it down to D and E. And from there, when I'm told that the hose poured 64 ounces per minute, I can plug that in and say that my time is equal to m divided by 64. But again, I still don't know what m is equal to, and so I'm still not able to solve for the rate. I'm sorry, I'm not able to solve for the time that's required for the hose to fill the bucket. So again, the answer here is going to be A. I can eliminate D. The answer is going to be A. And the key takeaways here are, number 1, to push the question, and number 2, I want to take the information and I want to put it in a format that looks like something I'm familiar with or something that I'm able to work with. With that in mind, I want to go ahead and take a look at the next question together. Again, I'll pop this one up on the screen, and then after I've left it up there for a moment, we'll come back and we'll talk through it together. Awesome. Hopefully you've had a second to work through this question. If not, then you can go ahead and pause this video at this point and we'll go ahead and discuss the solution. But the question asks, it says a thief steals from a bank and flees the scene at 80 miles per hour. 15 minutes later, the police arrive at the scene and begin to pursue the thief at 120 miles per hour. And it asks, how far does the thief flee in miles before he gets caught? And so we'll go ahead and we'll break this one down. And again, the truth is that this is actually a fairly easy question once you understand how to do it. And we'll get into some harder questions a little bit later in the video, but this question overall is not all that difficult, although you can see some variations of this question at different points throughout the GMAT. But I want to go ahead and discuss this one on the board. And so again, typically, there are two different ways to approach this. One is to say this, and this is probably the most common thing that we see from students, is something like the distance is equal to the rate times the time, and both of these two distances are actually equal. So the rate of the thief, which is 80 miles per hour, times the time of the thief is equal to the rate of the police, which is 120, times the time of the thief minus 1/4. And you are totally able, because the police have a 15-minute delay, and you say that the distances coincide, or that the distances are equal, so you can set up this equality, and then you can kind of solve. You've got one equation with one variable, and you're able to solve that. I actually don't recommend that approach. So what I'm going to recommend is a little bit more of a logical approach, which I think can be more efficient and get you to the answer a bit quicker. And so what I would recommend is this, is number one, I would think about, well, what is the head start that the thief gets? And so when I think about the head start that the thief gets, I'm not going to, obviously 15-minute head start, and that's the most common thing that I hear, but I actually want to think about the head start in terms of distance. So the 15 minutes, that's a quarter of an hour at 80 miles per hour, it's going to be 1/4 of 80, which is going to be 20. So the thief has a 20-mile head start, 20 miles. Then I'm going to ask myself, well, what is the speed difference? And when I say the speed difference, I mean the difference in the speed of the two parties. So in this instance, the thief is going 80 miles per hour. The police are going 120 miles per hour. So the speed difference is going to be 40 miles per hour. With that in mind, I can then actually calculate what is the time to catch up. And the reason for that is this, is that if I can say that the police are closing in on the thief at 40 miles per hour and they have a 20-mile gap to close, well, how long is it going to take them? Well, it's going to take them half an hour, right? So the time to catch up is going to be 1/2 of an hour. Now, I could write that as 30 minutes, but I like to write half an hour because I know that all my speeds are in miles per hour, and just about everything other than that 15 minutes is in miles per hour. And so I want to make sure that my times are the same and that I'm not using hours in one place, minutes in another place. So the time to catch up, the time required to catch up is half an hour. Then I'm asked, how far does the thief flee in miles before he gets caught? Now, there are a couple ways I can approach this. I'm going to show you one way first. So the first thing I'm going to think about is, okay, the thief then flees 40 miles, right? Because half an hour at 80 miles per hour, 40 miles, plus the additional 20-mile head start. Because again, this is not the time total, this is the time to catch up. And the time to catch up starts from the point at which the police start. So that would be a total of 60 miles. And A is going to be the correct answer here. The other way for me to think about that, or even if I wanted to double check it as well, I know that the police and the thief should travel the same distance. And so I know the total traveling time for the police was actually just a half an hour, right? Because during the initial head start period, they weren't traveling at all. And again, this starts after the head start. That time to catch up starts after the head start. And so I can multiply that half an hour times their 120 mile per hour speed, and that gets me to 60 miles as well, and everything makes sense because they should both be traveling the same distance, and so 60 miles, A, is going to be the correct answer here, and that's how far the thief flees before he gets caught. And so again, those are the basics. That's how I'm going to approach this type of question. We'll see another one like this that's going to be a little bit more complicated a bit later in the video, and so stay tuned for that. And but again, it's these basic fundamentals are how I'm going to approach this type of question. I'm going to ask myself, what's the head start, what's the speed difference, and what's the time required to make up that head start, or the time to catch up. That's what I'm going to solve for last. Let's go ahead and let's take a look at another one. I'll pop it up on the screen here and then give you a moment to work through it. Okay, hopefully you've had a second to work through this one. The question says, if 6 identical machines working at the same constant rate can fill an order in 5 hours, how many additional machines running at the same rate would be required to fill the order in 2 fewer hours? So here what I'm going to do is I'm going to, again, like we did with the first question, I'm going to bring things into a format that I recognize a little bit more. So let's go ahead and take a look at this one on the board. What I'm told is that 6 identical machines working at the same rate. So I'm going to call R sub M the rate of one machine. And I know that 6 times R sub M times a time of 5, right? Because I know that my work is equal to my rate times my time. So 6 times the rate of one machine times 5 hours is equal to, and we could call it W, we could call it, there's all sorts of things that we could call it, but I'm just going to go ahead and call it 1. So 6 times the rate of one machine times 5 is equal to 1 order of production. What I'm asked is how many additional machines working at the same rate would be required to fill the order in 2 fewer hours. So in other words, X number of machines times the rate of one machine times 2 fewer hours. So I'm not just going to use 2, I'm going to need 2 fewer than 5, right? So times 3 is equal to 1. And now all of a sudden here I have a system of 2 different equations, right? So I'm going to solve this one first, which tells me that the rate of one machine is going to be equal to 1 over 30, right? 6 times 5 is 30. Going to divide everything by 30. The rate of one machine is 1 over 30, which I can then use here and say X, which is the number of machines that I'm using here, times 1 over 30 times 3 is equal to 1. Again, here I'm going to be able to cancel that 3 with the 30, and so I have 1 over 10 times x is equal to 1. And so x should be equal to 10. Now, here's where hopefully if you got a chance to check out our arithmetic video where we discussed this at the very beginning, you'll go back, read the question one more time, make sure you're answering the right question, and remember that it asks you how many additional machines would be required to fill the order. So I started with 6 machines, I ended up with 10 machines, so I need a total of 4 additional machines. And the correct answer here is going to be B, which is 4. And so that's how many additional machines would be required. Again, the takeaway here is similar to question number 1, where what do I want to do? Well, don't panic. This question looks intimidating. Really, though, what I'm going to do, just like I'm going to do with just about any identical rate question, is I'm going to say, okay, here's the rate of one machine. I'm going to assign it a variable. In this case, that was R sub m. And then what I'm going to do is I'm going to look at it. I'm going to multiply it by 6 for the number of identical machines that I have, and then work through it and use it in this form of work is equal to the rate times the time, just like I did here. We'll go ahead and we'll take a look now at another question. And again, these are progressively going to get a bit harder. And so we'll go ahead and we'll take a look at one here next. Awesome. Hopefully you've had a second to work through this one. We'll go ahead and talk about it now. The question says, train A travels from Cincinnati to Columbus at 60 miles per hour. Half an hour later, train B travels from Columbus to Cincinnati. Shout out to the great state of Ohio, the Buckeye State, on the same tracks at 40 miles per hour, and 42 minutes after that, the trains collide. And the question asks, how long in miles is the track from Cincinnati to Columbus? Now, as we get ready to look at this one on the board, I want to say real quickly, I want to preface this by saying that this question is one that students love to bring up all the time. And it's one that they get very worried about. But the truth is that the fundamentals behind it are pretty easy. And not only are the fundamentals behind it pretty easy, but it really doesn't show up very often in actual GMAT official materials. We can think of 2, maybe 3 official questions out there. So it's not super, it's not super common. It's really actually pretty rare. But that being said, we'll cover it, and the fundamental skills behind this question are pretty straightforward and pretty simple. And so again, like we've done with previous questions, we're going to want to bring this thing into something that looks familiar to me. Again, because the fundamentals behind rates are pretty straightforward, pretty simple. And then from there, what we'll do is we'll begin to combine multiple parts of this question together. So let's start with this. It says train A travels, and again, I've abbreviated the question on the board here simply for the sake of room. As you can see, I almost ran out of room here at the bottom of the screen, at the bottom of the board. And so the reason that I say that is this, is that I want you, I don't want you to think that every word is not important or anything like that. I simply do it out of necessity. So, like we've emphasized in all of our videos, pay close attention to the wording of particular questions. What I'm told first is that train A travels from Cincinnati to Columbus at 60 miles per hour. So in theory, I could think about, I've got Cincinnati in one area, I've got Columbus in another area. I'm going here from Cincinnati to Columbus. A starts here in Cincinnati. Later on in the question, we'll learn that B starts here in Columbus and that these two trains are traveling towards each other. Now, what I know is that 60 mile per hour pace continues for half an hour before B even begins to travel. And so what I know is that in those 30 minutes, right, in that half an hour, that train A has already traveled 30 miles, right? And again, here, this is just distance is equal to my rate times my time. So from here then, though, I'm told that train B also starts to travel from Columbus to Cincinnati on the same tracks at 40 miles per hour. So after this all takes place, all of a sudden I have the two trains traveling towards each other. Now, when I have the two trains traveling towards each other, what am I going to do? How am I going to consider that? Well, actually, it's pretty simple. I just have to add the rates, right? Because this one is traveling 60 miles per hour and this one is traveling 40 miles per hour. So when you bring those two together, right, the 60 miles per hour here, the 40 miles per hour here, what's going to happen is that they're going to travel towards each other at a total of 100 miles per hour. So they're traveling towards each other at 100 miles per hour. So that's going to be my rate. And I know that that continues for 42 minutes until they collide. So what I'm going to say is that my time is 42 over 60. And again, I'm going to write it as 42 over 60 because this is miles per hour, not miles per minute. Okay. When I begin to simplify things, what I know is that 42 is actually just going to be 14 times 3, right? So I can say that's 14 times 3, can take out a 3 here. I get 14 over 20, right, which is 7 times 2 over 10 times 2. And so I'm going to get 7 over 10 here, right? And from here, I'll go ahead and simplify. I'll take out a 0, and what I have is 10. I'll cancel my 100 with my 10, take out a 0, and what I have is 10 times 7. And so 10 times 7 is going to give me 70 miles. And what you can see here is that when they were traveling together, I just combined the rates, right? Because they're both working towards the same end. They're both working towards the same goal. And then I just multiplied that by the time, and I got the distance. And so that's a total of 70 miles. Now, I'm going to remember that I'm asked how long the track stretches from Cincinnati towards Columbus. And so I'm going to have to add back on this initial 30 miles, and 30 plus 70 is going to give me 100 miles, which is going to get me to answer choice letter D right here. And so it's going to be 100 miles. Now, again, a couple key takeaways on this particular question. First one is this. This question isn't all that common, and it gets blown way out of proportion. Students think it's way more common than it actually is. So don't freak out about any of that. But the second key takeaway here on this one is that when I have both trains traveling towards each other at the same time, I'm going to want to add those two rates together. Again, I didn't do that initially because it was kind of like a head start, like what we saw in the previous question. But or I guess like what we saw a couple questions ago. But I'm going to, after I have that head start and they're traveling together, I'm just going to add those two rates. So that's how we are going to handle a question about trains colliding or something of that sort. Again, it's very similar to, students often get very confused about it because you've got trains colliding, but it's actually really similar to if I were to say, machine A produces 60 pitas an hour, machine B produces 40 pitas an hour. How long does it take them make 100 pitas. Well, they're working towards the same end, so this one makes 60, this one makes 40, and it's going to take them 1 hour together to make 100 pitas. So anyway, that is that question. I want to go ahead and pop another one up here on the screen, and once again, take a second, work through it. After you've had a second to work through it, we'll come back and we'll talk about it together on the screen. And again, we're getting into the portion of this video that starts to get a little bit harder. So, don't freak out if you're shooting for, a 44 to 47 or, mid 40s. We're starting to get into the, 48, 49, 50, 51 sort of range in terms of the difficulty level of questions that you're going to see. Let's go ahead and take a look at this one together. Awesome. Hopefully you've had a second to work through this one. If not, you can go ahead and pause the video at this point and hop back on for the explanation when you're ready. The question here says that Ahab ran southeast at 10 kilometers per hour. An hour later, Eli ran southeast along the same route as Ahab at 15 kilometers per hour. It says if Eli arrived at his destination 30 minutes before Ahab arrived at the same destination, how long in hours was Ahab's journey? So again, this one has elements of the catch-up question that we did earlier. And then this one also looks somewhat intimidating. But again, like just about every rates question that there is out there, once you start to break this thing down to the fundamentals, into the basics, you're actually able to work through it in a way that makes things a little bit easier on you. So I want to start with this. I know that Ahab ran southeast at 10 kilometers per hour. So again here, just like we did on the last question, I'm going to want to start with what is my head start. And I'm told that 1 hour later, so in other words, I have a 1 hour head start at 10 kilometers per hour. My head start is going to be 10 kilometers. Next thing that I'm going to ask myself is 1 hour later, Eli ran southeast along the same route at 15 kilometers per hour. So the speed difference is the next thing I'll ask myself for. 15 kilometers per hour minus the 10 kilometers per hour is going to be 5 kilometers per hour. And then I'm told that, that I want to know what's going to be the time to catch up. Well, and here what I know is that the time to catch up is going to be 10 kilometers, catch up at 5 kilometers per hour. The time to catch up here is going to be 2 hours, which typically pretty straightforward catch-up question. That's about all you're going to need to do. But there's some extra layers of difficulty here. And so we've got that basic information. Now I want to work from that basic information that we have and see if we can work through the rest of the question. So what I'm told is Eli arrived 30 minutes before Ahab. And so if Eli arrived 30 minutes before Ahab, then it took Ahab an additional 30 minutes to finish. right? And if it took Ahab an additional 30 minutes to finish, then what that means is how far ahead was Eli when they actually completed the journey? Well, I know that Ahab was running at 10 kilometers per hour. If he was running at 10 kilometers per hour for half an hour, right, then what I'm going to find is that Ahab ran a total of 5 kilometers at the end. So now I know that Eli finished 5 kilometers ahead of Ahab. Well, from here, what I'm going to do is I'm going to use a little bit of logic. I'm going to use a little bit of intuition. And I'm also going to use some math. And I'm going to, as is common on the GMAT, right? Once you start to get into these harder questions, it's a little bit less straightforward. And you start having to combine some logic, some algebra, and kind of work those two together. But what I know is this, is if Eli finished 5 kilometers ahead, well, I know their speed difference was 5 kilometers. And I know that Eli essentially took not only, so I know that Eli took 2 hours to get even. And if their speed difference was 5 kilometers an hour, then after another hour, he will be 5 kilometers ahead. And again, I know that it took Ahab 5 kilometers at the end to finish. So I know that Eli finished 5 kilometers ahead. So the time it would have taken him to get 5 kilometers ahead is it took him 2 hours to get even, 3 hours for Eli to get 5 kilometers ahead, right? And so after 3 hours, he's gotten 5 kilometers ahead. Well, what I know here then is this, is that Eli went for a total of 3 hours. 3 hours at 15 kilometers per hour tells me that Eli, and again, there's multiple paths to this solution here, so you may have worked through it a little bit of a different way at the end here, but I know that 3 hours at 15 kilometers per hour, distance is equal to my rate times my time. I'm sorry, that's actually my time times my rate is equal to my distance. And so 3 times 15 is going to be 45 kilometers. Now that's the total distance that Eli went, but that's also the same distance that Ahab went as well. So if Ahab went the same distance as Eli, then, and because I'm told that he was running along the same route and from the same starting point, then what I know is this, is that for Ahab going 10 kilometers per hour as his rate times his time is going to be equal to a distance of 45, which tells me that his time is going to be 45 over 10, or 4.5. And again, that's solving for Ahab's time, and so I'm going to say that the right answer here is D. So again, that's an example of a question where I use some of the catch-up, but I also, you notice there that we don't apply it in a super robotic fashion. I mean, sure, we go through the same steps initially, but at the end, we have to tack on a little bit of algebra. And that's often the case, a little bit of logic. We have to tack on a little bit of logic on top of our algebra. And that's often the case on the GMAT, is that you'll end up having to tack on a little bit of logic on top of the algebra that you do. So with that in mind, I want to take a look at another question here. I'll pop it up on the screen. And like I said, we're getting into the harder portion of this video. And so don't be discouraged if you start to struggle with some of these, because they are a bit more challenging. And so I'll go ahead and pop this one up on the screen and give you a second to work through it. Awesome. Hopefully you've had a second to work through this one. The question says, Jose drove to the store and returned along the same route. Did Jose drive the entire journey at an average speed greater than 50 kilometers per hour? Then I've got statement 1, Jose returned from the store at an average speed less than 70 kilometers per hour. And statement 2, Jose drove to the store at an average speed of less than 35 kilometers per hour. So what I'm going to do here is I'm going to take a look at this one on the board, and we'll talk through it a bit together. Now, when I think about this one, obviously I'm going to write AD over BCE here as I work through some data sufficiency. And again, there is a little bit of pushing the question that can be done here, right? Which is simply this. I know that average speed is equal to my total distance over my total time. And I could potentially push this a little bit further, and I could say, that my total distance is 2d over my total time. And this is where people can get a little bit, this could be t1 plus t2. Or the other way I could think about this is 2d over, if I wanted to, because distance is equal to rate times time. Time is then equal to distance over rate. So I could say this is equal to distance over rate 1 plus distance over rate 2. But again, it's, I have most of that in my mind, so I don't necessarily need to push through all that. But statement 1 tells me Jose returned from the store at an average speed less than 70 kilometers per hour. And again, the question asks if the entire journey was at an average speed greater than 50 kilometers per hour. So, it's pretty clear that statement 1 is not going to be sufficient, right? He could have driven 65 kilometers per hour both ways, or he could have driven, 2 kilometers per hour both ways. So it could easily be above or below 50 kilometers per hour. So I'm able to eliminate AD pretty swiftly here. Statement 2 tells me that Jose drove to the store at an average speed of less than 35 kilometers per hour. And that's where I'm going to start to think through this one a little bit with a little bit more of a thought. Because in theory, if the average speed was less than 35 kilometers per hour, that does put some sort of limit on my total average speed. So I'm told that he drove to the store at that rate. What I'm going to do here is I'm going to start to work through this a little bit and say that my average speed is going to be equal to 2 times my distance, right, over my distance over rate 1. And I'm going to say, in theory, the max for rate 1 is going to be 35 kilometers per hour plus distance over rate 2. And I still don't know anything about rate 2. I could go ahead and simplify here, right? I've got a d in every term, and that d in every term is going to cancel. From here, I can start to combine like terms by finding some sort of common denominator, right? So I'm going to have 2 over, and what I'm going to do is I'm going to combine these two terms. So I'm going to have rate 2 plus 35 over 35 times rate 2, right? And that's just simply simplifying these two, multiplying the second term by 35 over 35 and multiplying this first term by rate 2 over rate 2. From there, what I can do is then obviously I can flip and I can multiply. So I'm going to have 2 times 35 rate 2 over rate 2 plus 35, which is equal to 70 times my second rate over rate 2 plus 35. And again, I'm not super concerned about, am I spending too much time on this quite yet? And part of the reason for that is simply this, that I actually know for sure that with what I'm doing here, that this could potentially be helpful when I combine these two statements together anyway. And so I'm going to go ahead and I'm going to say, okay, so this is definitely worthwhile for me. From here, I get to this point where I have 70 times rate 2 over my second rate plus 35. And the question is, and again, I'm gonna erase some of this work that I did earlier here, but the question is whether that value can actually be greater than 50. And so what I'm going to do is I'm just going to set up an inequality for myself. And I'm going to say, can 70 times rate 2 be greater than, 70 times rate 2 divided by rate 2 plus 35, can that be greater than 50? And again, that's my question. And so from here, I can start to multiply things out. And what I get is that 70, and I'm going to keep in mind, this is just a question. That's why I wrote the question mark, that this is just a question. This is not given information. The question is whether 70 times my second rate or my rate of my return trip can be greater than 50 times rate 2 plus 35 times 50. I'm going to go ahead and leave that like that for just a second. And again, this is my question. My question now becomes, is 20 times rate 2 greater than 35 times 50? Which again is a question here. And then from here, I can go ahead, I can eliminate a 0 on both sides. And what the question becomes is rate 2, and I'll divide both sides by 2 here, greater than 35 times 5. Now 35 times 2 is going to be 70. 35 times 4 is going to be 140 plus 35. So 175, right, is rate 2 greater than 175 over 2. And that becomes my question, right? I can take this one step further and actually divide by 175 over, by 175 over 2, which is going to give me 67 and a half. Yep, 67 and a half. I'm sorry, not 67 and a half. Is my second rate greater than 87.5? Becomes my question. Okay, and from here, what I can do is that I can say, this has become my question. So I want to take a step back and just break down a couple of the things that we've done that students at times can have a problem with. And that's this. So number one, a lot of students will say, well, how is it that you can say that the rate was 35 and not when it says that the rate is less than 35? In theory, what I'm trying to figure out is the maximum rate, okay? So I'm trying to figure out the maximum rate because I want to know if the average speed could be greater than 50 kilometers per hour. So I want to figure out the maximum rate, which is why the maximum rate on the way to the store is 35. So that's why I assigned it as 35. Now, in theory, whatever value I get is technically not possible. It has to be just like 0.00001 less than that. But what I was doing is I was saying, what's my maximum rate? What's my ceiling? And the answer is not going to be inclusive of that ceiling, but what's my ceiling, right? So that's why I assigned 35. Now, again, this was me taking the information that I'm given from this statement, plugging it back into my question, and I get to the question, is my second rate greater than 87.5 kilometers per hour? Now, with just statement 2 alone, I actually don't know, and I think I eliminated my AD over BC when I was erasing here. So let me go ahead and toss these back up here. We already eliminated AD. And so because I actually, with statement 2 alone, can't say whether my second rate is greater than 87.5 miles per hour, then I'm going to be able to eliminate B as well. Because what I found from statement 2 is that if the average speed on the way home was 35 kilometers per hour, Then the average, or the average speed on the way there was 35 kilometers per hour. Then the average speed on the way home, in order for the average speed for the entire journey to be 50 kilometers per hour, must have been at least 87.5 kilometers per hour. So the average speed on the way back must have been at least 87.5 if the average speed on the way there was 35 in order for this all to work out. So the reason that I say that is this, and the reason that that's important is this, is I want to keep in mind, I don't want to get too detached from the question and turn this thing into all purely math. The other thing to know is that average speed, even if I have two equal distances, I can't just split the average speed in half and say I have an average speed of 50 and I have an average speed of 30 and say the average speed is halfway in between, it's 40. That's not true if you're going the same distances with each, okay? Because average speed is total distance over total time. If that concept is confusing to you, go back and watch our video on conversions in rates 1, and we address a problem like that in that video, okay? But average speed is not that simple. And so what I'm told is that if I've got an average speed on the way home, on the way to the store of 35 kilometers per hour, then I need an average speed of at least 87.5 kilometers per hour on the way home in order to be greater than 50. When I combine these two statements together, here's what I find, is that Jose returned from the store at an average speed less than 70. Well, that right here answers my new question. I pushed the question with the information in statement 2. My new question has become, was the speed on the way home, was that greater than 87.5 kilometers per hour? And I'm told not only was it less than 87.5, it was less than 70. And so there's no possible way for this entire average speed to be greater than 50, okay? And to do that, or to illustrate that, I could, and again, I've simplified the question with statement 2, and I like approaching it that way a lot better. In theory, I could also think about this as, okay, I've got 2d over d over 70 plus d over 35, and max out both of those speeds. When I max out both of those, and go ahead and max out both of those speeds and say, okay, if I max out both of those speeds, in theory, what would my top average speed be? When I do that, what I find is when I combine these two, I'm going to get 2d over 3d over 70. I'm going to then flip and multiply. And what I'm going to find is that my maximum possible average speed is going to be whatever 2/3 of 70 is, right? And so I could say that 2/3 of 60 is going to be, if I take is 40, so 46.6 repeating is going to be the maximum average speed here. But again, that's less than 50. I could have just answered it by saying that the average speed on the way home was less than 87.5 kilometers per hour. So a couple of different ways that you could look at that one there. And I think that the first one's a little bit of a more advanced way to look at that. You could also look at it this way. But you can see one good takeaway there is just how we took the information given to us in statement 2, and we really took that information and then reframed our question using that information, because that can also oftentimes be a very practical and a very helpful skill to apply here on the GMAT. With that in mind, let's go ahead and I want to take a look at another question together. I'll pop this one up on the screen. And again, we're getting into advanced questions. This one's pretty advanced. These next few that we're going to see are pretty advanced as well. So if you're shooting 44 to 47, really up to a 47, maybe even 48 on the GMAT, then these questions are getting pretty advanced for you that we're looking at here. So I'll go ahead and pop this up on the screen and give you a second to work through it. Okay, awesome. Hopefully you've had a second to work through this one. Here is what the question says. It says a partially clogged hose fills part of a tank with a capacity of X gallons of water at 5 gallons per minute. After filling 25 gallons, the hose clears up and fills the remainder of the tank at its normal rate of 10 gallons per minute. The time required for the hose to fill the tank was what % greater than it would have been had the hose never been clogged? So what we'll do here is, like some of these earlier questions, just take it step by step, because again, many of these rates questions, when you boil them down to the fundamentals, are not actually that hard. So when we think about this, we're asked to compare two different times. So I'm going to stay focused on the times. First thing is I'm going to think about the time given that the hose was clogged. And so what I'm going to do here is I'm going to say this, that while the hose was clogged, I know that I filled 25 gallons. So that's going to be work equal to my rate times my time. My rate was 5 gallons. My time was t. And so I get that my time is equal to 5 minutes. Then on top of that, I know that I fill the remainder of the tank at, which is going to be X gallons minus the initial 25 gallons that were filled. That's going to be filled at a rate of 10 gallons per minute times, and I'll call this T2 just to distinguish that it's a different time. And so my second time is going to be equal to X minus 25 over 10. From here, I know that the total time to fill the tank, given that the hose was clogged, is 5 plus X minus 25 over 10, or I can simplify and I can say that my initial time plus that second time is really going to be equal to, and I can make this a common denominator, right? Multiply the top and the bottom by 10, say that it's going to be 50, all this thing over 10, plus X minus 25 over 10, or 25 plus X over 10. Now I'm asked to compare that time to the time had the hose never been clogged. And so what I'm going to do here is I'm going to look at, okay, what if the hose were never clogged? And if the hose were never clogged, then the work would just be X gallons. The rate would be 10 gallons per minute. And the time, I'll call that T3, although I probably could come up with a better variable, but I'll call that T3. We'll say that my third time then is going to be equal to, the time if it were never clogged is going to be equal to X over 10. And so what the question says is it asks me, this time is what % greater than this time? And with that in mind, I'm actually going to begin to set this up. And essentially what I'm going to do is I'm going to divide the two by each other. So I'm going to go ahead and erase some of this earlier work. And what I can do is I can say 25 plus X over 10. And I want to divide that whole thing by X over 10. Because again, that would be the time with it being clogged over the time if it were never clogged. The other thing I want to do is I'm just going to take note that it says was what % greater than, not what % of. Because it says what % greater than, that actually means that I'm going to subtract 1 at the end, because 50% greater than would be 150% of. If you're not familiar with that, check out our percents video where we dive into that. But that is covered in that video, so I'm not going to get too deep into that. From here, what I'm going to do is I'm going to start to simplify. And I'm going to try and get an answer that looks a little bit more like what I've got down here. And so I'm going to flip and multiply. So I'm going to get 25 plus X over 10 times 10 over X. My 10s cancel, and I obviously subtract 1 still at the end. What I'm then going to do is I'm going to break this thing up into parts. So I'm going to say 25 over X plus X over X minus 1. The nice thing here is that this one and this one are going to cancel, right? Because this is equal to 1, so that cancels with that. And then all I'm left with is 25 over x. So then the question becomes, is it 25 over x percent? Is it 250 over x percent? Or is it 2500 over x percent? And what it's actually going to be here is this is going to be 2500 over x percent, because again, this isn't, had I followed this same method and gotten an answer like 1, well, that would be 100% greater than. Or had I gotten an answer like 3, that would be 300% greater than. And so when I get an answer of 25 over x, that's going to be, just like with those, I multiplied 3 by 100, I multiplied, right? If I got 0.03, then that would be 3% greater than. Right, so I multiply by 100 for each of those. In each of those instances, I would multiply by 100. So I do the same thing here, and I get 2,500 when I convert it into a percent, and I get 2,500 over x percent. Again, great example of a question that looks easy, but even though it looks fairly easy, even though it looks fairly straightforward, and looks like a question that is pretty easy to solve, or even looks pretty complex and looks pretty challenging, even though it looks like that, it actually becomes easy and it becomes straightforward when you just take it step by step, put it in a format that you're familiar with, and work it out from there. With that in mind, I want to go through here and I want to take a look at another one. We've got 2 more questions, and again, each of these are going to be pretty challenging. Awesome. Hopefully you've had a second to work through this one. I want to go ahead and take a look at it together. It says a distance runner ran the second half of a 40-kilometer race at an average speed that was 6 kilometers per hour slower than he ran during the first half of the race. If the second half of the race took 3 hours longer than the first half, how long in hours did he take to run the first half of the race? So it seems like a lot here to sort through, but again, as we've kind of been saying throughout this video, a lot of these hard rates questions boil down to the basics, so we'll see what we can do to simplify it. Let's go ahead and take a look at it together on the board. Once again, I've simplified it here as I've written it to hopefully conserve some space and leave myself some space to work through it. But the basic formula that we're going to want to use here all the way throughout, and not that we want to over-rely on formulas, but it's just about the only formula we have when it comes to rate, is this is that distance is equal to your rate times your time. And so I can say that 20, because I'm splitting this race into halves, 20 is equal to the rate of the first half times the time that it took in the first half. I can also say that 20 is equal to, and this is where I'm going to start to apply the information I learned about the second half of the race. So 20 is also equal to the rate of the first half minus 6, because 6 kilometers slower in the second half, times the time of the first half plus 3. And again, that's because the second half took 3 hours longer. From here, I've actually got something that I can work with, and I can begin to simplify things a bit. What I'll notice is that 20 is equal to R1 times T1 minus 6t1 plus 3r1 minus 18. And from here, what I can do is I know that r1 times t1, I know this from up here, I learned this earlier, that's actually equal to 20. And so these two are going to cancel with each other. I can go ahead and cancel with those two, and now I've got an equation with two variables, but I want to make it an equation with one variable, so I'm going to go ahead and I'm going to take some information, once again, that I learned earlier, and I'm going to do this with it. I'm going to say that, and again, it takes, not that this saves you all that much time, but it is worth noting that I want to solve in the end for T1, right? I want to know what my time, so that's not the one I want to substitute for then. What I want to substitute for is R1. And I want to say that R1 is going to be equal to 20 over T1. I'm also going to, at the same time, factor out a 3 here. So I've got a 3 in every term. I'm going to divide the whole equation by 3. I've just got 0 on this side. So I'm going to say that I have minus 2 T1, because I divided that by 3, plus, and I'm going to say 20 over T1, right, because I substituted that for R1 here, minus, and then again, I divided that by 3, but I'm also going to go ahead and just call that 6, because 18 divided by 3 is 6, right? So from here, what I'm going to do is, I don't love having my time in the denominator here. It makes it really hard to solve for things. And this is a strategy I'm going to apply not just here, but I apply this a decent amount on there's plenty of questions where I use this. So if you ever end up in this sort of situation, what I'm going to do here is I'm just going to multiply everything by T1, right, to get the T1 out of the denominator. And what happens is this, is that I'm going to get 0 is equal to negative 2 T1 squared plus 20 minus 6T1. And again, that's because I multiplied everything by T1. From here, what I want to do is this, is that I want to bring everything to the other side because I don't love having the negative 2T1 squared. So I'm going to say 2 T1 squared plus 6T1 minus 20 is equal to 0. Again, fortunately here, I can divide everything by 2. From here, what I can say is that T1 squared plus 3T1 minus 10 is equal to 0. And here, all of a sudden, once again, I've got a quadratic. So what I want to do is I'm going to separate this out. I'm going to have T1 squared plus something, and I'm going to have T1 squared minus something because I need a negative at the end. Now I need two factors of 10 that have a difference of 3 in between them. And I'm going to want to, or that somehow are going to add up to plus 3. And so I'm going to say plus 5 and minus 2. So, and I'm sorry, I said T1 squared. I shouldn't have said T1 squared here. I just divide that up into T1 and T1, not T1 squared and T1 squared. From here, what I'm going to go ahead and do is this is T1 could be equal to negative 5 or 2. Obviously, you can't have negative time. So I can't say that it takes me negative 5 hours. So I'm going to say that it takes me 2 hours. And that is exactly what I'm going to choose here. So I'm going to go ahead and choose A. Once again, key on this one is this, is just take it step by step. Use all the information that you know. Remember, at some point you end up subbing in the information you have here, down here. So remember all the information that you have. Good takeaway here where you multiply everything by T1. But again, these rates questions that look to be very complex are actually pretty straightforward and pretty simple. And so I want to go ahead and we'll take a look at another one together. I will pop this one up on the screen, and then after I pop it up on the screen, we'll take a second and we'll talk through it together. This will be the last one that we'll go through coming up here. So let's take a look at it together. Awesome. Hopefully you've had a second to work through this one. The question says, a factory manager estimated the average productivity in widgets of factory employees by dividing their estimated daily total output in widgets by their estimated daily total hours. Was the manager's estimate within 10% of the actual productivity? Statement 1 tells me the daily total output estimate and the daily total hour estimate were each within 10% of the actual totals. And statement 2 tells me the manager overestimated the daily total output by 1,000 widgets and underestimated the daily total hours by 10 hours. So let's go ahead and let's take a look at this one on the board together. Once again, I have written it up here in an abbreviated fashion, which is not to say that every word is not important here. But what I want to start with is I want to think about what statement 1 really tells me. If the output estimate and the hour estimate were within 10% of actuals, well, then definitely it could be within 10% of the actual, right? Because it could be that they're both spot on, right? That would be within 10% of the actual. But there could be as much as a 10% error in each. Well, to maximize my error, if I think about this estimation of productivity, really what I've said is output is my work divided by my time, and that's equal to my rate or my productivity. So really what I've said here with statement 1 is this, is that my estimated rate, so I'm going to say this, R sub E, is going to be equal to, and then I have as much as 10% error that I can introduce into each of these elements, my work and my time. And so what I'm going to do is, obviously I could leave them as they are, and that's within 10%. But what I could do is I could say maybe that my work was a 10% overestimate and my time was a 10% underestimate. And if that's the case, and that's how I'm going to maximize how far off I am, right? Because if I overestimated work and time, then sure, I increase my numerator, but I also increase my denominator, right? To maximize the difference, I want to increase my numerator and decrease my denominator, or flip it, right? I could do 0.9W over 1.1T. But for the sake of this, right, I'm saying that I increased my estimate, increased my work by 10%, and it decreased my time by 10%. And what I find is that when I do that, that's greater than 10% away from work over time. And the reason I know that is because work over time, 10% away would be 1.1 times work over time. But not only have I done that, I've also decreased the denominator by 10%, which is going to only increase the overall estimated rate even further. And so I know for sure that it's possible to be outside of 10% of the actual. And so I can go ahead and eliminate A and D here. Then I move on to B, C, and E with statement 2. And what statement 2 tells me is this, is that the manager overestimated output by 1,000 widgets. So my estimate output was the actual widgets plus 1,000 divided by the time, which was underestimated by 10 hours. So time minus 10. Now, here's the thing. So that's a change, and that change in terms of percent of the whole, I don't actually know if this is really like, I can't really say if this is within 10% of the actual. Because let's say the actual work was a billion and the time was a billion. Well, then 1,010, those are very small, I'm not very far away from the actual in the grand scheme of things, percentage-wise. I'm not really 10% off, right? But if the work was 1 and the time was, the time can't be 1 because you can't have negative time, but time was 11 or something, then all of a sudden I've shifted my time a ton and I've shifted my work a ton. And so now all of a sudden what I know is that it could actually be greater than 10% for sure. Because, if my work was 1 and I increased it by 1,000 widgets, that's a very significant percentage decrease. So again, I'm using logic here more than math, but that's because that's probably the most efficient way to do things. Again, if I went through actually plugging in values, I'm giving you examples, but I'm not plugging in values and I'm giving you examples to help you think through it logically. And so I can eliminate statement 2 alone and say that's not sufficient. And again, this is where logic comes into play with rates. Now, when I look at these two statements together, things start to get interesting. So I'm told that the output estimate was within 10% of the actuals. Well, what I could say then is this, is that 1,000 is equal to 10%, right? Because I still know for sure, because I'm told within 10%, I still know for sure that this could be super close to the actual, and I could definitely be within 10% of the actual. I'm confident about that. My question in my mind at this point is, can I be outside of 10% of the actual? Because this could, again, like if this was infinity plus 1,000, you know, in the grand scheme of things, that doesn't make a big difference, right? Or infinity minus 10, you know, that in the grand scheme of things, that doesn't make a big difference. And so that's why here I say I'm looking to see if it's possible at all that I'm outside of the 10%. I know I could be within it. Could I be outside of it when I look at these two together? Well, to get outside it, I'm going to want my 1,000 as significant as possible. So I'm going to say 1,000 is that 10%, is actually 10% of the actual. And so we could then say that the actual work was, we could say that our actual work was, if 1,000 is 10% of it, then we'd say that the actual work was 10,000, right? And if the time is within 10%, well, I underestimated the time by 10 hours. Okay, so I could say then that that time that was underestimated by 10 hours, that 10 hours was 10% of the time, which means the total time was 100 hours. Well, here, what I can say then is that my actual estimate, I can compare my estimate versus my actual. Okay, so my actual is going to be 10,000 over 100. But then my estimate is going to be, remember I overestimated by 1,000 widgets, 11,000, and I underestimated by 10 hours. So this is my estimated rate, and this is my actual rate. So my actual rate here, I can eliminate a couple zeros, is going to be 100. My estimated rate here is going to be 1,100 over 9. And so again, this is where a couple different things that I could do here to sort through this. I mean, I could say long division. I could say, there's a few different ways that I could think about it, right? I could actually do the long division here. For me, in my head, all I'm going to do is I'm going to say, well, within 10% of this actual rate, the most it could be, the max the estimate could be to be within 10% is 110. That's the maximum value that I could have to be within 10%. So is 1,100 over 9, is that less than 110? And what happens is if I were to do the long division here, right, 1,100 over 9, 1, 9, 20, that's going to be 2, 18, and that's going to be another 2. And so it's going to be 122.2 repeating is going to be the overestimate. Now, here's why that's important. Because to have 10% error, I need to be within 110. This is going to go far beyond 110. 122 obviously is greater than 110. So I have greater than 10% error is possible. And so I'm going to say C is out, could be within, could be without 10% error. And E is going to be the correct answer here. Again, this is one where there's a lot of logic that comes into play. There's a lot of thinking that needs to be done. Again, these last few questions were very challenging. And so, and they were meant to provide you with a little bit of a challenge. So if you breeze through them, great. If not, don't worry. These aren't necessarily questions that if you're looking to get a 47 on quant, maybe even a 48 that you necessarily need to be able to work through super easily. I hope this video has been helpful to you. Again, some major takeaways here is in our second rates video are this. Number one, you're going to want to push the question, as we saw in several of these data sufficiency questions. Number two, that a lot of these hard rate questions, and this is really the main takeaway, a lot of these hard rate questions come back to the fundamentals. And so when you reduce things to their fundamentals, and reduce these questions that are disguised or look challenging in different ways to the fundamentals, you're actually able to work through it and get to a pretty decent solution. As I said, I hope you've enjoyed this video. I hope this video has been helpful to you. Be sure to join us next time and for our next video, and we look forward to seeing you further.